5 sentences. Okay, it is my pleasure to introduce today's speaker, Professor Dan De Laurentiis, who is going to talk to us about the challenges and opportunities of systems of systems.
Thank you. Hello, everyone. Welcome. It's a nice opportunity for me to speak to the seminar. Just so I know who I'm speaking with, let's see, any students here from College of Engineering? Okay, a couple, and the rest from computer science, perhaps? Computer information technology, I heard? Okay. Any aerospace engineers? All right. I like to be the only one in the room. So, this is me. I live in Armstrong Hall, and it wasn't a great opportunity to talk to you about something that I think is relevant to all of the disciplines that you may represent. With a title and a topic like System of Systems, pretty much there's nothing that's not involved. That's the best way I can put it. So it's been an exciting 9 years that I've been here at Purdue. Of course, the last few have been in the wonderful Armstrong Hall. That I need to change my picture because it's not shown here. I need to address that. One of the proudest things that I've accomplished here is been chosen as a faculty fellow in CERIAS. So I think when you see the topic that I'm talking about, you might see the natural way in which the things we do in this area have a direct relevance to information assurance and related topics, which again is one reason I'm probably here speaking with you. So with that introduction, let me go directly to the advertising. Okay, so we concluded that I was the only aerospace engineer here, but I teach a course in a topic that's of course dear to my heart on system of systems modeling and analysis. And this course, which is offered every spring, from the very inception of this course back in 2006, was intended to reach as broad an audience as possible. And so I am hoping, now that I've memorized every face here in the room, that I will see some of you next semester or maybe in a future semester. I consistently certainly have students in this course from all the departments or the schools in engineering, and have had a few outside of engineering, including a few students from Krannert. So I continue to desire this to be a much broader participation. And even though problems related to aviation and aerospace have many examples of system of systems, we tackle projects in this class from a range of domains, from water and civil infrastructure, computer systems, certainly aerospace, defense, aviation, all forms of transportation, and even there's some space exploration. So it really has turned out to be a course that I think fulfills a lot of interest among students. So that's my advertising. You have my contact information. Certainly can find me on Google, so don't hesitate to email or come to visit me if you have more questions about the course. Okay, that's the 30-second advertisement that you get for watching the rest of this video. So a little context before I dig in. By the way, so this talk by design, and again, because perhaps we're coming from some diverse areas. This is a very high-level talk meant to kind of motivate you and answer some basic questions like I put in the abstract about what exactly is meant by this term system of systems. So there's nothing deep here, but hopefully there's some deep things we're doing in the research among several faculty across campus. And again, an opportunity maybe if something piques your interest, we can talk more and you can take some courses and maybe do some research. So this all started back in 2003 timeframe, where Purdue's College of Engineering decided to start hiring some of their new faculty members in a different way. Instead of just replacing Professor Smith after Professor Smith retires after 90 years on the faculty, they said, let's look across some of the cross-cutting areas like you see on the left column here, or the left-hand side, the rows. Energy systems, sustainable systems, healthcare, blah, 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 blah. And actually one of the selected focus areas was system of systems. So I got lucky. I was doing some work in that area while at Georgia Tech, and I came here and been working on it ever since. And I actually created this slide to drive home the point that, and I think you'll see it in the discussion we have today, that this topic is not exclusively and sometimes not even centrally about engineering or engineered systems. It's about policy at many different levels, from policies in the details of communication systems all the way up to national and global policy of how things work together. Economics, which are often major drivers in not only the commercial systems but even in the military systems, and I'll touch on that. And then, of course, operations, which includes human beings playing a role as participants and shapers of the system of systems. So this is one reason why I designed that graduate course that I mentioned in a very broad way, because we're not going to make progress on these kinds of things if we have consistently only a group of aerospace or aerospace and mechanical engineers working on them. So hopefully, I guess it's more advertising for you. But this has been my vision since I've been here, and it's something I continue to pursue. And I think it's resonated with a lot of people. Now, one of the things I thought to address up front, again, not in a very academic or pedantic way, but sort of what is the notion of a definition for system of systems? Well, I thought this might be one way to do it, and it actually, the title implies that it's related to a topic, an area of discipline called systems engineering. It's a really fascinating topic to talk about systems with people, because it could mean anything from a system administrator running a computer network all the way to the program manager or chief engineer for a major development program, and everything in between. But really, at the top level, you can think about those items on the left, very large, often complex in and of themselves systems. But we would typically always think about them, and we would develop them and design them as monolithic systems. Okay, so the airplane, in this case, I think that was a artist's conception of the Boeing 787, which is now flying after some rough roads, rough skies, as they like to say on the airplanes, rough air. Very complex, incredibly challenging. Obviously, it was 2 or 3 years late getting out, and then when it was rolled out, it had some issues with batteries, etc. So those are still very hard systems, and that's why most of our aerospace engineering and other kinds of students are still dedicated to understanding the basic physics and design theories behind those systems. The distinction we talk about with system of systems is that it's actually a distributed network of these kinds of large and small systems, perhaps, that are independently operating and essentially have their own reason for being in and of themselves, but occasionally are called together under some policy regime to collaborate. Why? Because there's a greater capability that can be achieved by the collaboration of those systems than anything done in isolation. Okay? So, again, distributed network of independently operating systems. This could apply to anything from a standard computer network, cloud computing, you name it. But the specific notion with the system of systems, at least in the world in which we operate is that these are hardware and software systems. So, big, heavy things that obey the main laws of physics that also have to be managed in terms of what information they're sharing with other systems. So I think I don't have to describe very deeply the fact that modern things that take place in the battlefield, whether it's in space or in air or on the ground, have a very strong, there's hardly anything that's done in those domains that doesn't have a system of systems character. I mentioned actually, perhaps believe it or not, and sometimes maybe from a distance, it doesn't seem like our space exploration programs are very much system of systems, and sometimes really they aren't. But we're finding that it's harder and harder to find the resources to have these large, expansive programs to explore places like Mars, especially with human beings. So one idea is to actually think of the problem of exploration as a human robotic system of systems concept that involves international partners very deeply as well. So a wide variety of opportunities, but the distinction, and again, I didn't intend to go very deep into literature or many concepts here, but when you think system of systems, think about not things on the left, but collections of those kinds of things on the left that occasionally work together to achieve some purpose. So sounds great, but there's this thing called emergent behavior that often gets in the way. Now, a little bit further, to give a little bit better sense of the different flavors of these kind of collaborative systems. This is one categorization among several that are out there in the literature, but this is one way to think about that central element of the definition, and that is, to what degree is there a centralized, singular objective for the participating systems? So, the first one is directed, where it says here, the objectives, management, funding, and authority are all at that single top level. So systems are subordinated to the SOS. So in some sense, I call that a degenerate system of systems, because if you think about that Boeing 787 example, that single airplane, I mean, it qualifies here, right? The entire aircraft is the sole reason for all the things inside the aircraft to exist. So a directed SOS is essentially a degenerate SOS or a monolithic system. But it's kind of good to have that as one of the extreme points in these definitions. Now the second one, where it starts to get more interesting, is the acknowledged category. So the SOS objectives, management, and funding and authority exist. However, the systems that are part of that SOS retain their own management. So remember that notion of independence of the systems? So this is where things get very interesting, and not only interesting from sort of the physics perspective of operability of a system of systems, but the policy and economics of this, right? So if you're in charge of developing system X, and it has its own purpose, and your success and your paycheck is dependent on the ability of system X to do its primary thing, how do you think you're going to react when you're also asked to change what you do sometimes to participate in this larger collaborative? You might be a little leery, right? And if no one forces you to be part of a directed, then there's issues of incentivizing participation in that SOS. Collaborative, basically, as we go down the list, it gets looser and looser centralized coordination. So collaborative implies that there are no objectives in management at the SOS level. Systems voluntarily work together to address shared or common interest. And finally, virtual is like collaboratives, but systems don't know about each other. So again, we can get into things like the internet, again, cloud computing and such as that. And so those on the lower level tend to be in those categories. Many of the examples of SOS that at least I deal with in the research I do in civil air transportation and military defense systems tend to be more on the acknowledged side. But it gets more interesting, especially when you think about, let's say, allied countries working together. It can get even more sometimes collaborative in the definition shown here. And so there's significant challenges in these problems depending on which type of SOS that you have. And sometimes the challenge is, what is the type of SOS that you would want to solve a particular problem? Okay, so with that very top-level notion of SOS, I'd like to just give you a few snapshots of some ways that we are starting to describe them so that we can do problem solving, modeling and simulation first, and then problem solving. Actually, before I do that, and I should have done this first, how many people, by a show of hands, have heard of the term before you came to this seminar today? A system of systems. No? In what context did you hear?
It was software engineering class, and my professor asked a student to talk about and present a seminar, each student, and one of my classmates talked about that.
Oh. Well, now I feel bad because I'm sure that talk will be better than this one.
No,
Yeah.
it is not.
Thank you. Now, the person behind you, raised.
Not a specific instance, but I've seen it come up in the literature for information security a couple of times when we're dealing with systems.
Okay. It turns out that as a term in the literature, it actually has appeared and reappeared over the last 40 years in a few different contexts, computer systems, systems engineering and such. And when I first started getting involved, it was on the next wave of people rediscovering it as an important topic and arguing incessantly about the definition. And I finally got tired of that, so I just would go to a different session at the conference and actually do some work. So I think, but it's a term that does require some deeper description. And so one of the things that we actually developed was our own little, perhaps lexicon is a strong word because it's not as formal, but a way to very conceptually describe these kinds of problems, regardless of the type that they might be from the previous slide. So here you see the categories, and I kind of gave away my mentality early on that this is not just about developing the engineered systems and putting them together and then saying the problem is done. It really is considering design variables and objective functions that exist in the operations, the policy, and the economic domains. And so with a little touch of strategy, I ordered these 4 categories in the right way to call this the rope table. And the levels that you see indicated there in the colors and with the Greek symbols indicate that really the system of systems concept, kind of by its name, right? Its notion of hierarchy. And so we want to be very explicit about the hierarchy of systems that constitute what may be at whatever the top level is called a system of systems. So I'll just probably only have a brief opportunity to show a few slides on natural ways that we use to describe this hierarchy, including graphs, structured graphs. We do some work with Bayesian networks for analysis under uncertainty and such. So this is something we do. So as an example, and sort of a very dense chart, but this is just a notion of one of these rope tables, and this is typically one of the things we have students do right at the beginning of the course. This happens to be a rope table where we have the ROPE. Apparently I have an old slide where we had the categories not quite organized yet to spell rope. Darn it. And along the left, you see the different levels of essentially the hierarchy. So just for example, the notion here is just to give you some sense of an example. So for air transportation, if you think about physical resources, all of us have flown, I'm sure. So you think about physical resources at what we would call an elementary system level. We started with things like vehicles, like airplanes, runways, control towers, etc. And then across the different column, across the 3 other columns are the specific descriptions and then eventually design variables that are related to operating, incentivizing, and conducting policies on the operation and the economics of those particular resources. Now, as an example of going to the next step, what we would call a beta level network is some kind of graph representing a linkage between elements of resources at the alpha level. And the particular topology and dynamics that operate on that network, again, are developed based on knowledge of the operations, the economics, and the policies that are either in place if you're examining an existing system of systems, or as design variables to see if you could improve the performance of the system of systems going forward. And we happen to put some names on these networks for air transportation and use goofy pictures of travelers and pilots. And probably 15 or so years, when we take pilots out of the airplanes and just have autonomous flying commercial aircraft, we'll take those pictures out. No one even blinked. Someone's smiling. How many of you sitting here right now would be comfortable getting on board a commercial flight that is being flown autonomously? Raise your hand if you would be comfortable with that. I'll call that about 2.5 people. I was at a conference recently, and the NASA administrator felt that within 10 to 15 years he would be on a flight that had that feature. I was very surprised to hear him say that. I don't agree with him, but he either misspoke or he was very optimistic. Interesting reason I asked that, and it's not unrelated to system of systems, because eventually we're going to talk about topics related to autonomous sensor networks and such, and tracking architecture, surveillance. But any modern commercial jet has automation on board and flight control systems that allow the aircraft to really fly on autopilot or automatically in any flight mode. In fact, there was some criticism in some accidents of why the pilots were actually landing an aircraft manually when it can be done safely. Part of it is the nature of pilots, right? Think of if you were a pilot, you probably want to do something for your pay, and you also probably have a feeling that your training is still superior to that computer. So for landing and takeoff especially, I think pilots often are operating the aircraft. So it's not as far-fetched as one thinks from a technological perspective, but it's policy, legal, and otherwise implications. So anyway, and I also point out to the students, once they get happy with this wonderful rope diagram they made, this is not a depiction of a system of systems problems. At this level, with 4 or 5 levels and stuff, this is actually many system of systems problems that are embedded within this. Okay, so just a few descriptions of different networks that we could draw in something like air transportation, to include the fact that the airplanes basically transit and are operated on their own network. I think you all probably know the flight crews are operating on a different network, because you've probably been in the case where the airplane is sitting there in the sunshine waiting for you to come on board, and you're ready and everyone else is ready except there are no pilots available. That's because they're operating on a different network. So these networks interplay with each other, and since the nature of the system of systems is kind of this interoperating network of systems, we often use these networks as our main analysis topics. So one exemplar of why you should care about this, or why people are caring about these kinds of problems, and certainly people are thinking about these 2 problems I'm going to tell you in the system of systems context, but not always acting on them in that way, because there's still quite a bit ways to go in terms of tools for decision making that we need for these types of problems. But in case you are not aware, in the U.S. there is a big transformation in how air transportation takes place, and that's called next-gen. So the items on the left are the characteristics of today's air traffic control and air traffic management system. Ground-based, dependent on human interface. So we have ground-based radars, basically identifying where aircraft are in the sky, and that information is provided to air traffic controllers, who, by voice command, tell the pilots in the cockpit, basically from the runway all the way to the origin runway to the destination runway, where they should fly the airplane. Okay, so I used to say, I don't know if they do this anymore, but on United Airlines you can listen to channel 9 on their audio system, and you can basically hear how the pilot in many ways is just a instruction follower, where the air traffic control is instructing the very precise routing of the aircraft. Now, the so-called next-gen system will be based on satellite navigation, so GPS, right? If our phones have it, we might as well start using it for airplane separation and traffic management. Digital versus voice communication, collaborative operations with decisions made in the cockpit rather than the cockpit being told what to do, and thus flight crews having more control of their trajectories. One of the really contentious issues in this, though, is whether we can have a distributed separation assurance function. Okay? So right now, the reason air traffic controllers are doing all these things is to ensure that your airplane stays away from the other airplanes. I was going to use a more technical term when I called U.S. Airways once, and I said, "Why is my flight delayed? You know, it was on time 5 minutes ago, and the airplane's there." And she said, "Sir, there's an air traffic control delay, and what that means, sorry to get technical," she said, "but that means that we cannot allow your aircraft to bump into another one after it takes off." And I said, "Don't give me that technical jargon." But, of course, she was correct. Separation assurance. So now in a system in which the aircraft has very precise position and velocity information about itself, as well as position and velocity information about its neighboring aircraft, the task of ensuring separation can now be done between the aircraft rather than relying on ground control, which eliminates time delays, cost, etc., but is a very different paradigm than what we have today. And so then questions of safety come up, and air transportation and the FAA, in its role as protector of the flying public, has to pay attention to quantifying impacts of safety of new technologies. So back to policy, right, and economics, and engineering, and operations. Now, slightly different application, but very similar in many respects in terms of some of these rope categories. And a project that I'm leading here at Purdue is related to the missile defense application. So this is a picture I stole from the Missile Defense Agency's website. And basically, I think it's pretty easy to understand the problem. Our nation and other nations want to protect themselves against another nation, perhaps, or someone launching ballistic missiles our way. And so what you see here is a collection of interoperating and often independent systems that are intended to work together in order to provide that missile defense function. Now, at the top here are all the different kinds of sensors, and of course there probably are many others not shown here. They're shown on the top, and of course one of them might be a satellite, but naturally some of them are also located on the ground or at sea. And then in the middle here, essentially looking across, you can imagine this is an enemy threat. And there's various technologies that are available or being studied to shoot down those enemy missiles. This one's kind of perhaps the most fun. It's a massive laser that is on board a 747 aircraft. If they ever develop, it's basically a prototype right now. It's not operational, but if they ever do develop it, I hope the targeting mechanism is really good, because I'd hate for my house to be unintentionally microwaved by the laser. But one of the advantages of that kind of system, of course, it's very mobile, and as it's sort of intended to show, where's my mouse? Okay. The closer that you can intercept an enemy's missile, the better it is, right? Because that way, there's no you're destroying it before it ever gets to be threatening to your home territory. So that's one advantage of having potentially an airborne laser concept. And then there's a variety of missiles of various sizes that handle things more conventionally now. In what's called the mid-course, which typically takes place outside the atmosphere, there's a missile, and then if things aren't going very well and all those other things don't work, there are terminal defense systems. And then some of you who are old enough may remember from some of the Gulf Wars, the very end of the spectrum, when something is kind of raining down on you very close, is the Patriot-type missiles. which can be effective, but make you nervous, right? Because that's the last layer of defense. So everything I mentioned there is actually not the topic of the research we're doing, but on the other hand, everything is the topic of what we're doing, because we're working on what's closest to the intelligence of the system of systems, and that's the stuff at the bottom called command and control, battle management, and communications. So essentially, all of these wonderful hardware systems, remember these big monolithic resources that apply or follow Newton's laws and stuff, without the appropriate information and the timely information and the trusted information passed between them, none of it works. So really that's the point of our research and the notion of developing a system of systems architecture that makes all of this work. This is something that may not, now that I realize I have too much time to talk about, but I like to talk about it because of the title. It's called Pain Points. So all of those systems that I showed on the last slide in the missile defense application, there's really smart people in government and industry trying to develop those systems and get them built on time and on budget. But unfortunately, because of the nature of this kind of distributed network of independently developed systems, it gets very hard to do. So remember when I asked each of you to think of yourself as developing System X? So imagine you're developing this System X called a satellite, and you're really working hard to make sure it fulfills its requirements. And then the person developing the missile says, I need 15 new measurements from you. And you've just spent 8 years working with Raytheon developing your satellite for everything but those 15 requirements. Or the missile says, I wish I could tell you the requirements I need from you, but I'm 5 years behind schedule. So now you, who probably are perfectly on schedule, are going to get a delay and so these things spiral, and this is all in the context, by the way. Let me just hop one more time. Remember I talked about these monolithic systems? There is a single aircraft that's in development and getting close to operation for the U.S. government. You've probably heard of the F-35, the Joint Strike Fighter. When you look at bar charts of the amount of money spent on individual programs in the Department of Defense, that one is like 50%, and everything else is chunked together is 50%. So developing these single complex monolithic systems are already taking a huge budget challenge, and now System of Systems is bringing difficulty, but the reason we're after it, right, is because you can potentially get a much cheaper solution to a problem with a System of Systems capability than you can with these individually optimized expensive monolithic systems. Okay, now some of you might be working in information assurance and cybersecurity related research. So given all this background, I hope you see that our idea of a system of systems is very much reliant on this information and data exchange in an appropriate fashion. And so the key to resilient system of systems include the addressing of risk, which is a function of what the threat can do, the vulnerabilities of your systems and links, and the consequences of those. Anyone tackle the topic of resilience as an actual optimization problem in any courses you've taken? Information theory? Okay. So it's one of those terms, I do work in complexity and resilience. I do seem to do work in areas that have some broad domains to work in, which means it's very hard to read all the papers that you need to read, but it's also fun. Okay, skip that. Very simplistic things you certainly already know, but at least it's an entree to talk about this. So I've got this collection of interoperating systems in my SOS, and things that could go wrong, either because of some malicious action of an enemy, or perhaps even just Mother Nature, or Murphy, or something I've done. So I can have a link failure. So I gave the example, certainly in operation, if a satellite sensor has to give a position information to a missile, and that link is severed, if there's no other way for that information to get to the missile in a timely fashion, then there's going to be no chance of intercepting the enemy threat missile. You can have a node failure. So whichever kind of node and whichever way you define your graph or your network, obviously we have to deal with node failures as well as link failures. And actually those two are the easy ones, right? Even from reliability theory, or there's all kinds of stuff in graphs and network topologies and stuff where you can quantify resilience and impacts of sort of link and node failures. And then there's that ugly stuff in the middle, which is, what if I wasn't aware that a link that I'm relying on is being tampered with? Or what if I thought that the information I was sending across that link was private, but it was actually shared? Those are, of course, the very dangerous ones, and it puts a direct stress on the notion of a collaborative system of systems, or even a virtual one where you're thinking about collaborating with allies, right? Or even outside the military. Think about back to the air transportation problem. If you're now going to allow a set of aircraft in a geographic region to be responsible for separation, if there's an unintended miscommunication or mistranslation of some information, you could call that an infected link. This could be very problematic. So, again, very high level, why system of systems can be challenging and vexing. I mentioned pretty much all of this here. This is kind of my jumping off slide to talk about some modeling and simulation. One interesting notion that, again, I mentioned briefly is the idea of complexity. And actually, there's many definitions of complexity. We think that complexity is one of the axes of response that you're concerned about when you're designing an architecture for system of systems. The definition given here is actually sort of based on information, the amount of information necessary to describe the regularities in the system effectively. And for neophytes to this area, I try to tell them about the Rube Goldberg competition, which is, kind of the opposite end of the spectrum, where you're intentionally trying to maximize complexity. And I tell outsiders that Purdue is the best in the nation, the Rube Goldberg competition. However, when we're designing architectures for system of systems, we want the appropriate amount of complexity. That is, not too much and not too little. And we want to understand the interrelationship between complexity and resilience, because complexity and the amount of information necessary to understand your system implies different levels of vulnerability. So it's another topic we cover in the course. There are other people at Purdue, even within domains that you might be involved with, that are working on system of systems, sometimes explicitly, sometimes less explicitly. And some of the things that are, some of the topics and areas of research that are being investigated for this context include optimization, game theory, behavioral decision making. You can read the list. I talked about networks and modeling and simulation extensively. And hopefully by now, even with this short introduction, many of these would appear to be very natural to you to study in this area. One interesting one I can mention, I think within the family of game theory, writ large, there's something called mechanism design, which is actually how would you design a game in order to have participants play the game to achieve some desired outcome at the global level. And so basically, how would you allow people to do what they want to do naturally or share what they want to share naturally in order to achieve the objective? And I have a student who's doing a master's thesis on that, and we're trying to incorporate some of that. So if you happen to be someone who knows about that or is interested in that topic, I'd love to talk with you and introduce you to some of our students in my group. But many of these others are important. Certainly we mentioned the behavioral part. Frankly, I think that's a topic that is massively understudied, probably across many disciplines, but certainly this topic area. How does a human being, I even still tend to think, no matter how much I told you about how open-minded I am in resources and economics, but the actual modeling of a human decision maker and how they respond to information in different contexts is critical to how these system of systems eventually work, but not studied very deeply. Unless some of you are, I'd love to hear about it. Okay, what is this crazy flowchart doing here? This is one example of a research project that we're working on that is trying to make some headway into getting some of that formalism and that usefulness in terms of decision-making aids in this topic area. So the bottom line of what this is all saying is there's people in this red circle that are on the front lines of developing a system of systems capability. It could be in the military, it could be in civil infrastructure, it could be an energy grid, it could be roads, transportation, water. They are the ones struggling with all those hard problems that I told you about, where they're trying to get something to work that requires 15 other things that they don't control. But they're trying to incentivize, make policy that encourages participation in the right way, reduce vulnerabilities, etc. So while they're doing that, we thought we would try to help them out a little bit by providing this notion of an analytic workbench. If any of you are familiar with any of the various maybe Purdue Hub, what do you call them, portals, we're actually thinking that this could be something like that, where we have a set of analytical tools that can, given the inputs and the expectations of the problem that the user has, we can apply these analysis tools and give them guidance on how they should change their architecture. In other words, how the graph of the system of systems is actually structured, or the policies that imply how the graph actually evolves. How could they make changes that would give them a better outcome, basically? And so that's the notion. I don't have time in this talk to talk about some of the tools. I'll mention them briefly on the next slide. And the other thing we're doing is you get an answer from there, but you'd like to have some sense of the robustness of that answer. So one thing that we're working on in a couple different areas are using simulations. And in our case, we do a lot of agent-based modeling, where we test out what those alternate architectures might actually do in a synthetic world that looks something like, and we hope is congruent with, the actual real world. So all of this sounds great, and we're getting a lot of great feedback. People are very excited about this. But lurking behind it, when some people are really honest, in some applications, decision makers at upper levels are uncomfortable using black box decision-making tools. And that's an unsolved problem, right? You know, how do you display confidence in a very detailed, analysis tool that you're not going to understand completely all of its details, but yet you understand it and trust it enough to actually make decisions on it? And if we can't solve that, then we're really back to square one, where the decision maker is, trusting their gut. And even they know that they're not happy with that. So again, I've already mentioned there's some very typical questions that an SOS engineer might ask, or an SOS analyst. And certainly things like, is my system of systems, which is requiring extensive space-based communications, is it vulnerable to infected links, failed nodes, etc.? Let's see. Some of the methods we're working on in this toolbox and testing are using Bayes nets, robust portfolio optimization, colored Petri nets, and some modified versions of redundancy and reliability. Anyone using Bayes nets here in their work? No? Yes? No? Okay. Anyway, just to give you a sampling, and if you know of some better tools that after seeing 18 of my slides, you're dying to tell me that you have a perfect method, I am all ears. So yeah, we're developing, trying to develop a comprehensive yet simple set of inputs that people can come to this workbench with and use a variety of the tools. Yeah, I just thought that this idea of of networks deserves some more attention, and we do somewhat 3 or 4 weeks in the graduate course I teach on studying some of the new concepts out of network science and how people look at the structures of graphs as predictors of the evolution of some dynamic taking place on the graph. And one thing I start out with here in terms of how we could do this is, given the way I've described system of systems, I hope you're convinced that this is not something, a system of systems is not something that you just build brand new, right? In other words, all that stuff about the next-gen air transportation system, it doesn't mean that we're going to turn off the system next February, send everyone home and start taking the train, work on it for 5 years with new technologies and new policies, and then turn it back on. We can't do that. We won't do that. And so how can we gather data on the existing system of systems and do some machine learning, whatever you want to bring to the table, to understand what are some of the patterns in some of these networks so that we can understand better the design variables for making the system better. So that's sort of what's going on up here. And we do actually a couple things once we take some snapshots of that kind of data. First, we look at the issue of complexity. So is there a way to quantify a network complexity that teaches you something and is a valid metric for doing design with? And then we get into the world of dynamics, where we actually look at how these networks actually evolve over time. And if we're really good and lucky, we can actually develop some enduring principles, which you might call a working theory for how networks are a basis for analyzing system of systems. So that's what we try to do there, and it's not easy, but it's fun. And again, the topic on the network science side, you could read everything from biological networks to computer networks, social networks. You can calculate, how many degrees you're separated from your favorite scientist. The possibilities are endless. I mentioned Bayesian nets. This is something we've looked at in terms of understanding the criticality of systems. So here we have a little example. It's probably even too hard to read, but think of one of these military systems where you have several ships and helicopters and satellites and underwater systems, and they're all trying to accomplish a mission, but you're not quite sure that you've linked them together in a way that gives you an appropriate level of resilience. And perhaps the first question you have is, what's the worst possible day I can have in terms of a node failure? Which system can go down? And then you can walk down the hall and talk to the person in charge of that system and threaten them, right? Saying a lot of bad things are going to happen to you if your system fails. And if that doesn't work, then buy them candy. I don't know. Whatever you need to do, you cannot allow your most critical systems to fail. And then we're also generating different patterns of what we call resilience patterns that actually shows how a system might degrade first and then completely fall apart under different scenarios of partial system failure. So I'm very convinced, and we know that there's people in other fields that actually do similar kinds of things. It's just that in some of the system of systems, the types of failures or degradations are a little bit different and not always based on the physics, right? It could be based on the budget or the policy. I think this is probably one of my last. We're doing some work on consensus control for sensor networks, which are often part, like on the missile defense problem. And again here, whether you have a direct collaboration or the virtual SOS where you're not even aware of another sensor that might be adding information to some problem, how do you come to consensus in tracking a target, for example? How do you account for bias and sensor measurement errors? And so there's some extended and robust Kalman filtering on a consensus basis that we're working on. Again, I'm sure and I know at Purdue there's some sensor networks work going on as well. Boy, this one's in here, and hopefully these slides will be available to you. This is a wonderful slide. I could teach an entire course on just parts of this. Professor Solberg, who's now retired from our School of Industrial Engineering, put this together, and it's like a wonderful journey through some advanced modeling and simulation techniques over the last 60 years, leading to not all of them being replaced by systems, but actually the notion that we could use some of these techniques in new ways to tackle this problem. Exactly. I heard that up front. So, big picture summary, blah, blah, blah. I said this today. There's a few minutes left, maybe one. I've already asked you some questions, but any pressing questions? Anyone want to raise their hand and say, this is the best thing I've ever seen? Or you're crazy? Or something? Going once? Going twice?
Do you do any work with Homeland Security?
Could you use your microphone, please? Thank you.
Do you do any work with Homeland Security, or is it mainly defense?
Been mainly defense. But I know there's Homeland Security expertise and actually a center on command and control and visualization here, the Vaccine Center, that Professor Ebert and I have worked together, but I would like more. 10 seconds. Any other questions? You know where to find me. Please don't hesitate. Thank you for your attention very much.